The KLEP system operates on a straightforward concept, the interaction between keys and locks. These elements are foundational to how KLEP processes decisions and actions. Essentially, keys and locks require just a name and an attraction value to function within KLEP. For instance, if you wish to move an agent forward in a game space upon pressing the W key, you simply release a key named W key. This key, when recognized by a corresponding lock, triggers an executable that propels the agent forward. This basic mechanism of key to lock interaction, which governs the execution of actions, forms the bedrock of KLEP. Yet it's the diverse application of this mechanism that introduces complexity. So, let's begin. In my design, locks and keys are represented as scriptable objects. This approach particularly benefits locks, as designing them beforehand allows for a more streamlined development process. When designing locks, I focus on specifying the types of keys that they should respond to, thus setting the stage for how actions will be triggered. On the other hand, keys often, but not always, emerge dynamically during gameplay, generated by code and introduced into the system as needed. A lock consists of two main components: the lock itself, which includes its name and attraction value, and a list of KLEP conditions. These conditions act like the pins in a traditional lock, requiring specific keys, or more accurately, the information those keys carry, to align correctly for the lock to open. It's within these KLEP conditions that the actual comparison and decision-making process occur. Sometimes the condition might be as straightforward as checking for the presence or absence of a particular key in the neuron. For example, a key labeled took damage underscore key could activate a lock tied to a defensive action. The scope of comparisons within the KLEP system extend far beyond basic key presence or absence. Keys serve as conduits for varied and complex information, which means that the comparison process can involve any data conveyed by a key. This includes, but is not limited to, player position, the count of nearby allies, fluctuations in stock prices, or even the number of human faces detected by a guided missile prior to impact. Additionally, locks are not constrained to a single KLEP condition. They can encompass multiple conditions to suit complex decision-making scenarios. Moreover, KLEP conditions offer flexibility in their evaluation criteria. Not all conditions need to adhere to a strict all-or-nothing approach. In my design, any condition can be flagged as an OR condition, indicating that satisfying this condition or any other within the lock suffices to unlock it. This concept introduces two types of locks: loose locks, which require only one of their conditions to be met, and strong locks, which demand the fulfillment of all conditions. Such flexibility allows, for instance, a movement-related executable to activate when any key among the W, A, S, or D keys is present, further enabling it to execute specific logic based on which of those keys was detected. This executable with that lock can then be transferred to any KLEP system, and it will respond if a W, A, S, or D key is detected, and this can be done at runtime. KLEP lock features two main functions: is satisfied by agents and create unique instance. The later, create unique instance, operates exactly as named. When the unique instance required flag is set, either during setup or when a lock is acquired by an executable later, this function creates a deep copy of the lock for that specific executable. This capability ensures that runtime modifications to a lock, such as adjusting conditions to reflect weapon degradation, do not impact the broader system's logic. The function is satisfied by agent evaluates whether a set of conditions associated with the lock are satisfied by the provided set of keys. Here's how it operates. 1. No conditions means always satisfied. If the lock has no conditions, either it's null or empty, the function immediately returns true, meaning the lock is considered satisfied regardless of the key's presence. Separation of conditions. This function categorizes the conditions into two groups based on whether they are marked as is or conditions. Or conditions, conditions with the is or condition is true. These conditions allow the lock to be satisfied if any one of them is true. Non-or conditions, conditions where is or condition is false, these require all conditions to be true for the lock to be satisfied. Evaluating or conditions. If there are any or conditions, the function checks if any of these conditions are true given the set of keys. If at least one or condition is satisfied, the condition returns true, indicating the lock is satisfied. If no or conditions are met, the function concludes that the lock is not satisfied and returns false. Evaluating non-or conditions. If there are no or conditions, or if the or conditions are satisfied, the function proceeds to evaluate the non-or conditions. For the lock to be considered satisfied in this case, all non-or conditions must be met. The function checks this by ensuring that every non-or condition evaluates to true with the given set of keys. This logical structure allows for the lock to accommodate flexible logic, where certain conditions can independently satisfy the lock, or conditions, while others must be satisfied together, non-or conditions. This approach enables complex decision-making based on the presence or absence of specific keys within the system. The essence of KLEP lies in the concept of the key, which is both profoundly simple and intricately complex. A KLEP key requires only a name and an attractiveness value to function within the system. However, the flexibility of KLEP allows for more sophisticated handling of keys, leading to the introduction of the /key loader. The /key loader presents a significant advancement in the KLEP framework, enriching the system's capabilities by providing a structured method to manage a wide array of data that a key might carry. While the foundational role of a key remains straightforward, the loader, and by extension the property manager attached to each key, complicates it significantly. This component enables keys to carry detailed, structured information beyond their basic identifier of a name and an attraction, broadening the utility within the system. Despite the potential complexity introduced by these additional components, it's crucial to remember that at its heart, a KLEP key's necessity is minimal. A name and an attraction value suffice. The /key loader and the property manager serve to enhance the system's flexibility and depth, allowing for a richly detailed information exchange within the KLEP framework. This encapsulation of complexity within simplicity defines the elegance of the KLEP approach, marrying straightforward operational requirements with the potential for sophisticated data management and decision-making processes. The discussion of KLEP keys therefore embodies the dual nature of the system, accessible yet capable of profound complexity, driven by the innovative structure of the /key loader and the functionality it supports. The property manager system within KLEP represents a strategic balance between simplicity and flexibility. Initially, if your system's requirements are fixed to specific parameters, the /key loader and consequently the property manager in KLEP key can be bypassed, underscoring the system's inherent adaptability. The property manager's primary role is straightforward. It organizes properties. This system empowers designers to dynamically assign various data types. Examples: list of vectors, hash set of integers, booleans, dictionaries, any of it, as named variables within the KLEP framework. Consider a scenario where you're tasked with integrating data from a newly developed water testing technology into your system. Previously, this would necessitate a comprehensive overhaul to incorporate the new data and data types. With the introduction of /key loader, you simply adjust the expected properties in the loader, and subsequently, all keys managed by this loader will inherit these new properties. This functionality emerged from a practical need to incorporate a rotation field into keys without resorting to hard-coded solutions. Previously, essential data like lists of transforms or vectors were hard-coded into the keys. The current system, enhanced by default properties in the key loader, allow for the seamless addition of new properties. Even more, adjustments can be made at runtime to accommodate keys with previously unrecognized properties, emphasizing the system's dynamic nature and its capacity for growth and adaptation. Further discussions will dive deeper into the system's intricate capabilities and its significance in the broader KLEP framework. This wraps up our exploration of keys and locks within the KLEP framework. We've touched on the functionality and potential of the property manager and /key loader, but there's more depth to be explored in future discussions, including the /key manager component. While we've delved into the essence of what keys and locks are within KLEP, the life cycle of keys, how they're created, managed, and utilized, is going to be for another day when we're talking about /key manager. I hope this glimpse into KLEP's mechanics has sparked your curiosity, and for those eager to dive deeper, keep an eye out for my upcoming book. Buy my book! That will explore these topics in greater detail. In the meantime, your support through Ko-Fi is immensely appreciated, and for a hands-on look at KLEP's implementation, feel free to visit my GitHub page. Next video is /key manager and the key properties and the key loader. Thank you very much for your time. Thank you very much for your interest.